The concavity of a graph is talking about the curve of the graph. So you can have two different situations. Either the graph can be concave up. Concave up means curved upward. And curved upward can be f can be concave up and f is decreasing, or f can be concave up and f is increasing. Or you can have the graph being concave down. Concave down would be sketches like these, which f is concave down and f is increasing, or f is concave down and f is decreasing. So if the second derivative is positive, the second derivative being positive, it's the same thing as saying the first derivative is increasing, then f is considered to be concave up. And if the second derivative is negative, another way to say the second derivative is negative would be as if f prime was decreasing, then the f graph is concave down. So to test your function for concavity, the second derivative must exist. So you must be able to take the second derivative. If you can't take the second derivative, you cannot test for concavity. First thing you're going to look for is when is the second derivative equal to 0 or does not exist. That'll get you the possible inflection points. The next step is to make an f double prime number line. And if the second derivative is positive in that number line, then f is concave up. And if the second derivative is negative on that number line, then f is concave down. And the third thing is to determine that your inflection points actually occur where the concavity changes. So your possible inflection points will become actual inflection points where your concavity changes. And that's where f double prime changes signs. So for the first example, we're going to look at h of x is equal to 3x squared minus x to the third. Taking the derivative, we get 6x minus 3x squared, and then the second derivative gets us 6 minus 6x. Take that second derivative, set it equal to 0 or does not exist. Since we have a polynomial, we don't have to worry about does not exist. So then we get the critical possible inflection point, x is equal to 1. And that possible inflection point then can be abbreviated as the PIP, would be put on their second derivative number line. So our h double prime number line, that possible inflection point is put right on the h double prime number line. And we'll use a test number 0 and 2, and substituting that into the second derivative, get positive. Substituting in 2, we get negative. So we know h is concave up on the interval from negative infinity to 1, because h double prime is positive on that interval from negative infinity to negative 1. And then h is concave down on the interval from 1 to infinity, because h double prime is negative on the interval from 1 to infinity. And then the point of inflection, 1 comma, getting the y value, substituting that in to get 2. So the point 1 comma 2 is an actual inflection point, because h double prime changed signs at x is equal to 1. To see a sketch of what this will look like, we have that point 1 comma 2, concave up before the 1 comma 2, and concave down after the 1 comma 2. So to find out where g is concave up and concave down and the inflection points, take the first derivative, which is a product rule, so we have gf prime plus fg prime. Simplifying that, taking the second derivative, derivative e to the x is just e to the x, plus, and then again we have another product rule, so we have e to the x times 1 plus x e to the x. And then simplifying that, we have 2e to the x plus x e to the x, and then factoring out the e to the x that they both have in common. Setting each factor equal to 0, get a critical possible inflection point of x is equal to negative 2, and no inflection point from e to the x is equal to 0. So your possible inflection point goes on your g double prime number line, picking a test number before and after negative 2, and substituting that into the g double prime. So using the test number of negative 3 and 0, negative 3 into the second derivative gets negative, putting 0 in becomes positive. So then g is concave up on the interval from negative 2 to infinity, because g double prime is greater than 0 on the interval from negative 2 to infinity. And then g is concave down on the interval from negative infinity to negative 2, because g double prime is negative on the interval from negative infinity to negative 2. And the gene does have an inflection point at -2 comma, getting the y value by plugging into the original function, which is -2 e to the -2. And the reason why is because g double prime changes signs at x is equal to -2. Seeing a sketch of this, just using our calculator to assist us on getting an idea of what this is going to look like. We have this sketch. You can see that the graph is concave up after -2 and concave down before -2. Given f of x is equal to x to the 2/3, finding the first derivative, we get 2/3 x to the -1/3. The second derivative is -2/9 x to the -4/3. So we're going to set our second derivative equal to 0. Rewriting the problem to bring the 4/3 x to the 4/3 to the denominator. Cross multiply, we get x is equal to -2, which does not give us a possible inflection point. So now let's consider it does not exist. So when is the second derivative does not exist? As if the denominator were to equal 0, so if x were to equal to 0, we have a possible inflection point. Making an f double prime number line, putting our possible inflection point on there, using a test number before and after 0, and substituting that into the second derivative. -1 into the second derivative is going to make negative. +1 into the second derivative is also negative. So there are no inflection points because f double prime does not change signs. And from using our calculators, getting an image of what this is going to look like, we can see from the graph of f of x that f is concave down and then again concave down, so f double prime does not change signs. So f does not have an inflection point.